Hello everybody. In this video we are going to be looking at the solutions to the Honors Sound homework problems 6 through 10, and all of these problems will be dealing with the Doppler effect. Let's take a look at problem number 6. The predominant frequency of a certain fire engine's siren is 1,550 Hertz when at rest. They want to know, what frequency do you detect if you move with a speed of 30 meters per second? And the first part is going to ask if you're moving at 30 meters per second toward the fire engine. And then for part B, they want to know what frequency you detect if you're moving at 30 meters per second away from the fire engine. So let's take a look and see what we are given in this problem. We are given the frequency of the source, which is 1,550 Hertz. We are not given an air temperature, and I mentioned this in one of the other videos, but remember, if we're not given an air temperature, we're going to assume room temperature or 20 degrees Celsius. And the temperature at 20 degrees, or the airspeed, the speed of a sound wave, I'm going to get this right one of these days before I retire. I'm going to get this right. The speed of a sound wave at 20 degrees Celsius is 343 meters per second. So if I don't specify a temperature or a speed of the sound wave, we can assume that the air temperature is 20 degrees Celsius and the speed of the sound wave is 343 meters per second. And because the engine is at rest, I know that the velocity of the source is 0. So for the first part, we're going to find the frequency you detect if you are moving at a speed of 30 meters per second toward the fire engine. So if I'm moving toward the fire engine, my velocity is going to be 30 meters per second. And just a quick note here on the subscripts. Remember, the subscript O stands for the observer. The subscript S stands for the source. So my frequency of the observer is 30 meters per second. And remember, it's positive 30 meters per second, because our positive and negative signs are now relative to whether we're moving toward or away from the source and or the observer. So because I'm moving toward the fire engine, my velocity is positive. And we want to know what the frequency of the observer is. So I am going to be looking at my Doppler equation, and I don't have to do any rearranging for this first one. I know that the frequency of the observer, which is what I am looking for, is equal to the frequency of the source times v. Now this v is the speed of the sound wave. So my v without a subscript is the velocity of the sound wave. V sub O is the velocity of the observer, and V sub S is the velocity of the source. Aside from the signs of positive and negative, the tricky thing with these problems is making sure that you have all of your velocities sorted out, because we have 3 different velocities that we're talking about here. We're talking about the velocity of the sound wave, we're talking about the velocity of the observer, and the velocity of the source of the sound wave. So I know that the frequency of the source is 1,550 Hertz. The velocity of my sound wave is 343 meters per second. The velocity of the observer is 30 meters per second, divided by the velocity of the sound wave again, which is 343 meters per second, minus the velocity of the source, which is 0. When I do that math out, I'm going to get a frequency of 1,685 Hertz, or 1,690 Hertz, rounded to 3 sig figs. So although the siren is emitting a wave or a signal at 1,550 Hertz, I'm really detecting it at 1,685 Hertz because of the relative motion between the observer and the source. For part B of problem 6, the observer is now moving away from the stationary source, and their velocity is still 30.0 meters per second. But note here, the velocity has now become negative 30 meters per second because we are moving away from the source. Remember, if you're moving toward the source of the observer, your velocity is positive. If you're moving away, your velocity is negative. We are still looking for the frequency of the observer, and we are still using our Doppler formula as we did before. We're going to plug everything in the same way, but now note we do have to plug in a negative velocity for the velocity of the observer. Everything else remains the same. The velocity of the sound wave is still 343 meters per second because we're still at room temperature, and my source is still stationary, so its velocity is still 0. So when I now make my velocity of the observer negative 30.0 meters per second, I will be given a frequency of 1,414 hertz or 1,410 hertz rounded to 3 significant figures. Problem 7 says you are standing still. What frequency do you detect if a fire engine whose siren emits at 1550 hertz moves at a speed of 32 meters per second, A, toward you, and B, away from you? So this problem is very similar to the previous problem, but instead of the siren or the source being stationary and the observer moving, now the observer is stationary and the source is moving. So our frequency again is 1,550 hertz. The velocity is still going to be 343 meters per second because we are assuming room temperature of 20 degrees Celsius because we're not specifying anything else. And now the frequency or the velocity of the observer is 0. So now the observer is stationary. So if the source is moving toward the stationary observer, the velocity of the source is going to be 32 meters per second. And we are still looking for the frequency of the observer. We're still going to use our Doppler formula. Once again, we don't need to do any rearranging, so that makes life a little bit easier. We are going to plug in the frequency of the source of 1,550 hertz. We are going to plug in the speed of the sound wave, and remember our velocity here is the speed of the sound wave. So that's our velocity of the sound wave. Our observer is stationary, so the velocity of the observer is 0. And the source is moving toward the stationary observer. So my source is positive 32 meters per second because it's moving toward the observer. So on the bottom half of the equation, it's V minus VF. So I have 343 meters per second minus a positive 32 meters per second. When I do that math out, I'm going to have a frequency of 1,709 hertz, or in this case, I think to 2 significant figures should be 1,700 hertz. Part B of problem 7 asks us to find the observed frequency when the source is moving away from the stationary observer. So now that my source is moving away from the observer, the source's velocity is going to be negative 32 meters per second. It's going to be negative now because the source is moving away from the observer. Still looking for my observed frequency. Still don't need to do any rearranging for the Doppler formula. Again, the only difference here now is that for the velocity of the source, I have to plug in negative 32 meters per second. So the bottom half of this equation is going to be 343 meters per second minus negative 32 meters per second. And once I do out that math, I am going to have an observed frequency of 1,417 hertz, or 1,400 hertz rounded to 2 significant figures. Problem 8 tells us to compare the shift in frequency if a 2.0 times 10 to the third hertz source is moving toward you at 15 meters per second versus you moving toward the observer at 15 meters per second. They want to know, are the two frequencies exactly the same? Are they close? Then they want you to repeat the same calculation for 150 meters per second and repeat it again for 300 meters per second. So let's do the first part first. So the frequency of the source is 2.0 times 10 to the third hertz. Again, I'm not specifying an air temperature or a speed of the sound wave, so we're going to assume room temperature of 20 degrees Celsius, and the speed of the sound wave will be 343 meters per second. The velocity of the source is 15 meters per second, and the velocity of the observer when they are the one moving is 15 meters per second. So to do it for the 15 meter per second velocity, first I'm going to do the source moving at 15 meters per second and the observer being stationary. So if the source is moving toward the observer at 15 meters per second, note it is going to have a positive velocity because he's moving toward the observer. So when I plug everything into my formula, I have my frequency here, I have the speed of the sound wave. My observer in this case is stationary, and it is the source that is moving at positive 15 meters per second. When I do that out, I will get 2091 hertz, which would round to 2100 hertz to two significant figures. For the observer moving at 15 meters per second, so now my observer is moving and my source is stationary. So once again, I plug in my frequency of the source, the speed of the sound wave, but now my source is stationary, so their velocity is 0, and my observer is now moving, and their velocity is 15 meters per second. And now when I do that math out, my velocity is going, or my frequency, or the observed frequency, I should say, should be 2087 hertz, which rounds again to 2100 hertz. So the frequency shifts are going to be slightly different versus the source moving and the observer moving. They're very, very close to one another, but there are some slight differences. And you know, to two significant figures, they are the same, but there are some slight differences when we do out the calculations. For part B, we're going to repeat the same calculation, but we're going to change the velocity to 150 meters per second. So if the source is moving at 150 meters per second and the observer is stationary, everything else stays the same. We are keeping our Doppler formula. I'm going to plug in my frequency and my speed for the sound wave. My observer is stationary, so their velocity is still 0, but now the source is moving at 150 meters per second, and it's moving at a positive 150 meters per second because it is moving toward the observer. Again, remember that the negative sign here is built into the equation, but my velocity is still positive, so that's minus a positive 150 meters per second. When I plug all of this into the formula, I'm going to get a observed frequency of 3600 hertz, rounded to two significant figures. And now I'm going to repeat the operation, but now having the source be stationary and the observer moving toward the source at 150 meters per second. Once again, plugging in my frequency and velocity for the sound wave, but now my source is stationary, so their velocity is 0. My observer is moving toward the source at 150 meters per second, so again, their velocity is positive, so it's plus a positive 150 meters per second, and that will give me a observed frequency of 2900 hertz rounded to two significant figures. So notice that the difference in the frequency shifts is much, much larger now that the velocity, relative velocity, is greater between the observer and the source. We're going to do this one more time, but now increasing the relative velocity between the source and the observer to 300 meters per second. So now at 300 meters per second. Again, we are still using positive velocities because our source and observer are still going to be moving toward one another. For our first scenario, it is the source moving at 300 meters per second. So my source is moving and my observer is stationary. Still plugging in our frequency and the speed for the sound waves. Those haven't changed. Once again, my observer is stationary, so their velocity is 0, and my source is moving at 300 meters per second, so they are moving at a positive 300 meters per second because they're moving toward the observer. So we have 343 meters per second minus positive 300 meters per second. And that will give me a frequency of 1,953 hertz, or 16,000 hertz. Did I screw that up? I think I screwed that up. It would be 15,953 hertz, which would round to 16,000 hertz. Really should be one significant figure because it's 300 meters per second. But so that should really be 20,000 hertz realistically. Now for the observer moving at 300 meters per second. So now my observer is moving at 300 meters per second and my source is stationary at 0 meters per second. When I do that math out, my observed frequency is going to be 3,749 hertz, or I have 3,800 hertz here. It really should be 4,000 hertz to one significant figure because I am using 300 meters per second here, which is only one sig fig. But regardless, I think you can see that by increasing the speed now to 300 meters per second, that the change or the difference in the two frequencies has increased even more. So the faster you are moving, the greater that discrepancy is. Problem 9. An airplane traveling at half the speed of sound, which is 172 meters per second, emits a sound of frequency 5.00 kilohertz. At what frequency does a stationary listener hear the sound A as the plane approaches and B after it passes? So the velocity of the source of the sound wave, which is the plane, is 172 meters per second. The observer is stationary, so the velocity of the observer is 0. The speed of the sound wave is going to be 343 meters per second because we are not specifying a temperature or speed of sound. So that is going to be 343 meters per second. We're assuming room temperature. And the frequency emitted by the source is 5 kilohertz, or 5.00 times 10 to the third hertz. So the first thing we're going to do is calculate the observed frequency as the plane approaches the listener or the observer. So again, I'm going to use a Doppler equation. I'm going to put in the frequency and the speed of the sound wave. My observer is stationary, so their velocity is 0. And because the plane is approaching the observer, it's moving toward the observer, I'm going to use a positive value for its velocity. So the velocity of the source is going to be positive 172 meters per second. So again, on this bottom half of the equation, we have 343 meters per second minus a positive 172 meters per second. And when we do out that calculation, we are going to have an observed frequency of 10,029 hertz, or 10.0 kilohertz. Now, when the plane passes the observer, it is now going to be moving away from the observer. So now for the second half, after it passes, the plane is moving away from the observer. Everything stays the same in terms of the frequency, the speed of the sound wave, and the observer being stationary, but now the speed of the source, which is our plane, is going to be negative 172 meters per second because it is moving away from the observer. And because the plane is moving away from the observer, its velocity is now negative. So now on the bottom half of my equation, I'm going to have 343 meters per second minus a negative 172 meters per second. When I do that math out, I am now going to have an observed frequency of 3,330 hertz or 3.33 kilohertz. Problem number 10. A commuter train passes a passenger platform at a constant speed of 40.0 meters per second. The train horn is sounded at its characteristic frequency of 320 hertz. Well, first thing I want to know is what overall change in frequency is detected by a person on the platform as the train moves from approaching to receding. So the train is moving at 40 meters per second, and the train is our source. Actually, the whistle on the train is the source, but the whistle is moving the same speed as the train. That's 40 meters per second. The frequency emitted by the whistle is going to be 320 hertz. The observer is standing on the platform, so their velocity is 0. So the velocity of my observer is 0. And again, we're not specifying an air temperature, so we're going to assume room temperature of 20 degrees Celsius, which will make the velocity of the sound wave 343 meters per second. And what we are looking for is the change in frequency. So what is the observed frequency as the train is approaching versus what is the observed frequency as the train is moving away from the platform. So we're looking for the change in frequency, which we do represent with our delta. So first what we're going to do is find the frequency of the train as it is approaching. So when we look at our Doppler formula, we are going to plug in the frequency of the source, the speed of the sound wave, my observer, which is moving or which is stationary, so their velocity is 0. And because the train is approaching, the velocity of the source is going to be positive. So 343 meters per second minus a positive 40 meters per second. And that will give me an observed frequency of 362 hertz as the train is approaching. After the train passes the platform and is moving away from the observer now, so now the train is moving away from the observer. Again, I'm going to plug everything in the same. My frequency is the same. The speed of the sound wave is the same. The observer is still stationary, so their velocity is still 0. But now because the train is moving away from the observer, its velocity now becomes negative. So now we have 343 meters per second minus a negative 40 meters per second. And when that happens, we are going to have an observed frequency as the train is going away from the observer of 287 hertz. So the frequency as the train is approaching is 362 hertz. I should say the observed frequency is 362 hertz, and the observed frequency as the train is moving away is 287 hertz. So the change in frequency is going to be, again, change in frequency is going to be the frequency of the train as it is approaching minus the frequency or the observed frequency of the train as it is moving away. So 362 hertz minus 287 hertz is going to equal a change in frequency of 75 hertz. The second part of problem 10 asks what wavelength is detected by a person on the platform as the train approaches. So in order to find the wavelength, we need to use our wave speed formula. And I want to solve my wave speed formula for wavelength, which is a lambda. So I know that the wavelength is going to equal the velocity of the sound wave divided by the frequency of the sound wave. So the velocity of the sound wave is 343 meters per second. Now we have to use the observed frequency as the train approaches the platform because they are asking what wavelength is detected by a person on the platform, not what wavelength is emitted by the train. So we do want to use the observed frequency as the train approaches the platform, which was 362 hertz. So I divide my velocity by that frequency, and that will give me a observed wavelength of 0.95 meters.